Peatlands are the world's largest land-based carbon store. If we look after them properly, they absorb greenhouse gases from the atmosphere and slow down global warming. But if they get damaged by fires, farming, or climate change, they release more carbon from the soil in the form of carbon dioxide and methane. Unfortunately, there are still gaps in our understanding of exactly how local climate conditions affect the complex chemical and biological processes that control these emissions. One of the reasons for this is that peatlands are very difficult to monitor. They're incredibly fragile ecosystems, and the muddy bogs are often too deep to walk over. At the moment, most peatland researchers still visit sites in person to collect measurements. This is not ideal because doing so can disturb the peat, releasing trapped gases, and it's so slow and expensive that it often means we can only get a few readings per month or year. So, wouldn't it be great if we could get this crucial data remotely? Recent advances in sensor technology now mean that wireless sensor networks have the potential to do exactly that. For my PhD, I have designed and built 5 wireless boxes which measure carbon dioxide and methane levels, as well as local conditions, and upload all this data to the internet using mobile data. I took this network and deployed it in a New Forest peat bog for 2 months, collecting a total of over 7,500 data points during the study. A comparable traditional study would collect less than 50. So this gives us a lot of useful reference data that didn't exist for the site before. And one of the most interesting things we can see in the data are rapid spikes and dips in carbon dioxide and methane due to sunlight. These emissions follow a daily pattern which can be explained in 4 stages. First, sunlight increases photosynthesis in the leafy plants, which consumes carbon dioxide and accelerates the transport of methane through plant stems to the atmosphere. Next, increased sunlight and temperature stimulate methane conversion to carbon dioxide by peatland mosses. At the same time, temperature deeper in the peat, where methane is produced, rises more slowly than at the surface, causing a later spike in methane production. And finally, at night, all of these processes are less active, allowing carbon dioxide and methane levels to stabilise. It would not have been possible to observe the effects of these processes with traditional daily sampling rates. So in conclusion, this wireless sensor network offers a cheaper, safer, and more detailed way of monitoring peatland emissions. I plan to continue developing the system, adding even better sensors and improving the sampling rates further. It's my hope that future versions can be used to monitor and protect many more peatland sites by forecasting wildfires, identifying the best sites for restoration work, and improving global carbon dioxide and methane estimations. Thank you for listening.